Hey there, this is a brief presentation on how to calculate empirical and molecular formulas. Feel free to pause at any time to solve the problems on your own or to take your notes. First, let's define an empirical formula. This is a formula that shows the ratios of one element to another in the smallest whole number form. That last bit there in bold is quite important, especially when we get to what's called the molecular formula. For example, take a look at what's written in red. CH2 would be an empirical formula for the following compounds: C2H4, C3H6, C4H8. You can see it's almost a common denominator for the compounds. It's the most reduced form of that compound. Finding the empirical formula is important when we don't know the identity of a compound and we want to figure it out. And this is exactly what we've done in our empirical formula lab with the zinc chloride when we didn't know how many atoms of zinc combined with how many atoms of chlorine. So let's take a look at how we would do that. Let's say this was our problem. It says a sample of a compound is found to contain 1.472 grams of hydrogen, 35.072 grams of carbon, and 93.434 grams of oxygen. What is its empirical formula? The nice thing about empirical formulas is there is a series of a couple of steps that you can follow and pretty much find the solution every time. Step 1, find the moles of each element. Now you all know how to do this. We'll use the molar masses from the periodic table. So first, for hydrogen, I would start with my given mass, use hydrogen's molar mass, and then I would find the moles. Do the same thing for carbon, that it's almost 3 moles, and then finally oxygen, 5.8. If you need to review this math, I would pause this and go back and take a look again. You might also need to go back and watch the notes on atomic mass, moles, and molar mass. So that's step 1. Step 2, similar to our counting by weighing activity, which was an experience on relative mass, what we're going to do next is divide each of the numbers, each by the smallest number of moles. So our smallest one, if we consider our moles, we have 1.46, 2.9, and 5.8. The smallest is clearly hydrogen. So we'll basically divide each of them by hydrogen. 1.46 divided by 1.46 is, of course, 1. 2.9 divided by 1.4 is about 2. And notice that I'm keeping track of which elements I'm comparing here. And then finally, 5.8 divided by 1.4 is about 4. Now, I said approximately. If these numbers are really close to a whole number, then it's good enough to round. Usually these are based off of collected data in a lab, and we definitely make errors. So as long as it's pretty close to the number, you're safe to round. So now the next step is quite easy. We're basically saying that 1 mole of hydrogen combines with 2 moles of carbon and 4 moles of oxygen. So how do we then represent that in the actual formula? We use these mole ratios to fill in the subscripts. So we have a hydrogen, a carbon, and an oxygen. And hydrogen divided by itself is 1, of course. Carbon to hydrogen, we have 2 carbons. And oxygen to hydrogen, we have 4. Now remember, this is the simplest ratio. It's not the actual ratio necessarily, but it's the simplest ratio that these elements combine in. And that's how you do an empirical formula. It's pretty simple. But what if you don't get a whole number ratio? For example, what if you had a problem like this? Let's say we were looking at oxygen and phosphorus, and we ended up getting 2.5 to 1. That's not a whole number, and I'm not going to round up to 3. That would be very inaccurate. So what can we do to make it whole? Ponder that for a moment before you keep going. How about we multiply by a factor to make it whole? So in other words, we multiply both the top and bottom by the same number so that we don't change the actual ratio, but we've made it whole, because we definitely cannot have half of an atom. We know that. So I would say that if we multiply the top and bottom each by 2, we would get 5 to 2. So in other words, 5 moles of oxygen for every 2 moles of phosphorus. So with this now, Now we can use this ratio for our subscripts, and we'd get the empirical formula of P2O5. So that's how you do empirical formulas. Next up, molecular formulas. Now, what's the difference? They sound kind of similar. Molecular formula is basically giving the actual number of atoms of each element in one molecule of a specific compound. So compare these two compounds. We're all familiar with glucose from biology. We know its formula is C6H12O6. You can probably say that in your sleep. Well, if we take this very common known compound and we try to divide it by the biggest number that we can, we could divide the 6 and the 12 and the 6 all by 6 and get CH2O. In other words, one carbon for two hydrogens and one oxygen. That would be the empirical formula. So you can see that the molecular formula is the actual formula for the compound. Let's take a look at how to do that. In this problem, we're told that a substance has an empirical formula of CH2O and its molar mass is 180.15 grams per mole. What is the molecular formula? Now, in this case, the empirical formula has already been given to us, so we just have a couple of steps to get it to the molecular. And bottom line is we want to have some sort of a way to compare the molecular and empirical as a bridge. So this is how you'll do these. First step, find the molar mass of the empirical formula. We're already given the empirical formula and we're given the molar mass of the actual compound itself. So if I was able to find the molar mass of the empirical formula, well, then I could compare those two numbers. So I did this kind of all in one line here, but the molar mass of the CH2O, let's break it down. This first one is carbon. There's only one of them. We're going to add that to two hydrogen atoms or molar mass. And then we'll finally add that to one oxygen's molar mass. And you'd get a molar mass of 30.026 grams per mole. So now I have two numbers that I can compare. I have the molar mass of the actual compound, and I have the molar mass of the empirical formula. So step 2, divide the substance's molar mass, which was given, by the empirical formula's molar mass. So again, we're comparing, we're doing kind of a relative mass thing here. So we'll take the 180 of the molecular formula, so the molar mass of the molecular formula, divided by the molecular mass, the molar mass of the empirical formula. So 180 divided by 330 gives us a 6-to-1 ratio. So remember, round to the whole number quotient as long as it's close. Step 3, well, this is basically telling me that my molecular formula is 6 times bigger than the empirical formula. So I would multiply the subscripts in the empirical formula by a whole number quotient that I just found. So, oh, hey, this looks familiar. I would take 6 times CH2O and I would get our friend glucose. So again, this ratio really means that the molecular formula is 6 times heavier than the empirical formula. That is all, and I hope that helps you out. Again, you can watch this, take notes, and send me an email if you've got questions.